Hello friends, we are studying metric spaces, and last time we have defined metric, and we are studying some examples of metric spaces. Now I shall revise briefly the definition of metric. So it is a function, distance function from m cross m to non-negative real numbers, which satisfies the properties of row of xx is 0, x belongs to m, or here we will consider xyz belongs to m, and second row of xy is greater than 0, x not equal to y. Row of x and y is equal to row of y and x. This is for all xy belongs to m. And the fourth is the triangle inequality, that is row of x and y is less than or equal to row of x and z plus row of z and y. X, y, z belongs to m. So these are the properties to be satisfied by a metric. Then we say row is a metric. We have seen some examples, that is in R1 the absolute value metric, and then RD discrete metric, and then we have seen Rn Euclidean n space. Here the metric defined is absolute value metric, that is mod of absolute value of x minus y, and here RD, this example we have considered D we have defined from R cross R to as by in the definition non-negative real number, but d of x and y is equal to, or d of x and x is 0. Distance of x and x is 0 and distance of x and y is 1, x not equal to y. So this is the discrete metric space, and that discrete metric space is again on R. Last time in the last lecture I said it is on R2, but it is not on R2, but it is on R. So that is a correction in this example, and it is a metric space in R, and D is a metric. We have verified the properties. There I have told you that it is R2, but it is not R2, it is R only. This discrete metric space is in R, and the metric space is called discrete metric space and denoted by RD. So you should note this correction. Instead of R2, it is only R. This is the discrete metric space, and Rn also we have studied. Now we shall consider the next example, that is fourth example. Let L infinity denote the set of, this is a notation, denote the set of all bounded sequences. Bounded sequences of real numbers. First we consider a set. Here also we have considered the set R, here also R, and then the n dimensional space Rn. Here we are considering the set as L infinity. This is a notation, and that means set of all bounded sequences of real number. We know what is a bounded sequence. This sequence Sn is said to be bounded if absolute value of Sn is less than a certain number m. For all n belongs to R, then the sequence is said to be bounded. It has the lower bound and also upper bound. So that is the set of all bounded real sequences. And let x, now here we have considered the point as sequence. It is a set of sequences. So x we will denote the sequence xn, and n takes value 1 to infinity, and y the sequence yn. B, sequences, or that means we consider points. Here we have to consider points in the set in L infinity. Define we define row of x and y is equal to LUV of mod of or absolute value of xn minus yn, and this n takes values between 1 to infinity. So this is the definition of a metric, that is important. So two things are important, the set and then the metric defined. Now we have to verify this is a metric in the set or for the set L infinity. So that means this metric must satisfy these four properties, so that we can check. Now we shall verify. So row satisfies, whether this row satisfies the first property, it is obvious. Row of x and x, that is LUV of xn minus xn, that is 0, and thus least upper bound of the set of all elements is 0, then that is equal to 0. So we verify, or we see that so these are obvious, first three properties are obvious in metric. We see that row of x and x is this is LUV xn minus xn, and this is equal to 0. Row of x and y, this is again, and that if this x is different from y, then at least one xn minus yn is non-zero, and therefore the least upper bound is greater than 0 if x is not equal to y. And further also, row of x and y is LUV of absolute value of xn minus yn, but this is the same as absolute value of yn minus xn, and that is row of y and x. So thus first three properties are verified. Now the triangle inequality. So for triangle inequality we consider a number k. So what is important in these properties is triangle inequality. To verify triangle inequality, we consider let. Now consider for any k as a positive integer. Any k belongs to I, we have absolute value of xk minus yk. This we shall consider, and which can be expressed as absolute value of xk minus zk plus zk minus yk. Now easy to verify. This cancels and the value is the same. Further, this is, as we know, is less than or equal to absolute value of xk minus zk plus absolute value of zk minus yk. As this is the property we have seen in earlier lecture, absolute value of a plus b is always less than or equal to absolute value of a plus absolute value of b. And for this we can consider the least upper bound of this. So therefore if you write the LUV over all values of k from 1 to infinity, k lies between 1 to infinity, and if you take the least upper bound of all such values xk minus zk, then this value is a particular value, and here we are considering all values k for k taking 1 to infinity, and therefore this value is certainly less than this, because we are taking the least upper bound of the set, or roughly we are taking the maximum value. So this is the maximum value between when k takes values 1 to infinity, and therefore this value is less than or equal to this one, or therefore the relation remains again less than or equal to. And here also we shall have least upper bound zk minus yk, absolute value of zk minus yk. And but what is this according to the definition? This is the metric, definition of the metric. Instead of n, here we have used k, but it is the same as this, and therefore this will be row of x and z, and which is equal to row of x and z, and this is by the definition row of z and y. And you see what is the left side? Left side is absolute value of xk minus yk, and thus absolute value of xk minus yk is less than or equal to row of x and z plus row of z and y. Now we shall consider again here as k takes values from 1 to infinity, so as like this, and this implies, so this happens for all k belongs to I. This is true for all k belongs to I, and therefore this implies LUV of 1, k takes values between 1 to infinity of absolute difference of xk minus yk is less than or equal to row of x and z plus row of z and y. See what we have done for this. This is true for all k, and therefore if you take k between 1 to infinity, then this above relation remains true, and if you take the LUV of that, then that also holds. And what is this? This is row of x and y by definition. So thus that is row of x and y is less than or equal to, this is row of x and y, and this is less than or equal to row of x and z plus row of z and y. Now one thing is to be considered where x, y, z belongs to L infinity, or here we should consider let z is equal to zn. We are taking zn sequence, and that sequence belongs to L infinity. So this is to be noted. All the three elements are in L infinity. X is xn sequence, y is yn sequence, z is zn sequence, and thus we have proved the triangle inequality, and therefore this proves that rho is a metric. Hence rho is a metric. Rho, which is defined by the definition here, rho of xy. This definition was there. Rho of xy is LUV of absolute difference of xn minus y. Is a metric. Is a metric for L infinity, and this metric space is denoted by this metric space, actually L infinity rho, simply by L infinity. So this is the notation, and thus this is our next example for metric spaces. Now next we will consider one more example as fifth. Let L to denote. These are the notations used to specify a particular class of sequences. Let L2 denote the set of sequences x is equal to xn. So let L denote, or this L2 denotes the set of sequences x equal to xn. N takes value 1 to infinity, such that sigma xn square, n takes values 1 to infinity. This series less than infinity means convergent. So this is the notation. L2 is the set of sequences x, which is xn, sequences xn, such that summation xn square, infinite series of square terms of this sequence xn, is less than infinity means convergent. So such a set we have considered. Now we define a function rho for this and show that that is a metric. Define rho of x and y, or before that we should consider another point as let x be xn and y be the sequence y. Are in L2 means they satisfy the condition. Summation xn square is less than infinity, summation yn square is less than infinity. And now we define rho of x and y is equal to. So this we shall define in terms of norm. Norm 2 is equal to, say, norm of x minus y, norm 2 of x minus y. And what is the meaning of norm to x minus y? That we shall write as this is equal to. This is actually by definition. So summation x is a sequence xn. So this is xn minus yn. N takes value 1 to infinity and raised to half. As in Rn we have defined this type of metric. So this is norm 2 norm of x minus, that is the x and y, and its notation is norm of x minus y, and it is defined as summation xn minus yn square of xn minus yn and whole raised to 1 by 2. So then we shall show that this rho is a metric. Then rho is a metric. Now it is again easy to verify the first three properties of metric easily. That is, we have rho of x and x. So here we will consider for x, y belongs to L2, that is we have written earlier, and define this. So we have rho of x and x. See, in place of y, if we write x, then it becomes xn minus xn, and therefore it is 0. Rho of x and y. So this is as we see here, this is summation n takes value 1 to infinity square of xn minus yn, and this whole is raised to 1 by 2. Now we can interchange this in under square. So this can be written as summation n takes value 1 to infinity yn minus xn square of yn minus xn raised to half. Because a minus b, square of a minus b is same as square of b minus a, and thus this is rho of y and x. And second property is also obvious. This is greater than 0. If x is not equal to y, this difference is non-zero, and therefore this value is greater than 0. So rho of x and y is greater than 0, x not equal to y. So these three properties are easy to verify. Now what remains is the triangle inequality. So for triangle inequality we will consider now. let another sequence we shall consider as x and y we have considered here. We will take a sequence z. Now the sequence z can be taken as zn. Let z is equal to zn belongs to L2. And now we will have to show triangle inequality. We know that this is the triangle inequality, rho of x and y. Direct distance from x to y is always less than or equal to distance via z. That is distance of x to z plus distance of z to y. This is the triangle inequality. And now we will consider the left side as rho of x and y. By definition, this is norm of x minus y. Or now that can be written as norm of x minus y, or we will introduce z, x minus z plus z minus y. And there is property of norm similar to the property of absolute value function. Norm of s plus t is less than or equal to norm of s plus norm of t, and therefore this is less than or equal to norm of x minus z plus second norm, because the power is half here, square and then half power. So therefore it is the notation is second norm plus norm of z minus y. And here the property of norm used is norm of s plus t is less than or equal to norm s plus norm. So this is the property is proved in earlier chapter, infinite series. You may refer it. And but what is this? This is equal to rho of x and z, and this is rho of z and y. And thus you see the left side is this one, and the relation between these left side and the right side, extreme right side, is less than or equal to. And therefore rho of x and y, up to this it is equal, but then it becomes less than or these two are equal. So we use this symbol equal to and less than or equal to carefully. So these are exactly equal. This is less than or equal to, but again this means equal to rho of x and z, and this is rho of z and y. These are equal, but the relation between the first and the last becomes less than or equal to rho of x and z plus rho of z and y. Hence the triangle inequality is satisfied, and thus rho is a metric. All the four properties we have seen or verified, and this rho becomes a metric. Hence rho is a metric for L2. This metric space L2 and the metric rho defined by this way is denoted by L2. So thus these are some standard examples of metric spaces, definition and examples of metric spaces. Which metric spaces we have seen? R1, then absolute value metric, then here it is the metric is discrete metric RD, and then Euclidean n space Rn, and then L infinity, the set of all bounded sequences of real numbers, and then L2, the set of sequences such x such that summation xn square is less than infinity or convergent. So these are some standard examples of metric spaces. Now we shall consider example from exercise. So from the book from the book Methods of Real Analysis. So this is exercise 4.2. And the problem is, let L to L1. Let L1 be the class of all sequences Sn of real numbers. Real number such that summation of absolute value of Sn is less than infinity. What is the meaning of this? This sequence is absolutely convergent. Not the sequence but series. This series sigma Sn is absolutely convergent. Show that if we denote S by Sn and T as the sequence Tm are in L1, then this function rho of S and T is equal to summation n takes value 1 to infinity absolute value of Sn minus Tn define symmetric for L1. So this is the example problem from the exercise. Now it is not difficult to solve it. See, this is the function defined, and we have to show this function is a metric, means it satisfies the 4 properties required for a metric. I will verify one by one, and the first 3 are easy in every metric. Only what is important is the triangle inequality. So solution for the problem is, we have by taking these notations we directly write, we have rho of the first property, rho of SS. The notation here, the sequences are denoted by S and T. So we take rho of S and S. This is equal to summation n takes value 1 to infinity Sn minus Sn. And this is 0. Sum over 0, each term is 0. And that is 0. First property is satisfied. And now what about the second? Rho of S and T, and this is the same definition, summation n takes value 1 to infinity of Sn minus Tl, and this is not 0 or greater than 0 absolute value it is if S is not equal to T. This is not equal to 0 or greater than 0 if S is not equal to T. And therefore the second property is satisfied. At least one Sk is different from Tk if S is not equal to T. Therefore at least one value in the sum is non-zero, and therefore the sum becomes greater than 0. Second property is verified. Now the third property is symmetric property, that is distance between S and T is same as distance between T and S, or rho of S and T is same as rho of T and S. It is obvious. So this is summation absolute value of Sn minus Tn, and this absolute value can be written as absolute value of Tn minus Sn, and which is same as rho of T and S. and this holds for ST belongs to L1. Now the triangle inequality. So this is important to verify. But we have considered earlier examples and there these properties occurred. Three elements we have to consider, or 3 points we have to consider in the matrix spaces. Let S and T are as given in the problem. We will consider U here. Let U is UN sequence. N belongs to, N takes values 1 to infinity. This belongs to L. Third sequence we have considered S, T and U. Now what we have to prove is then row of S and T is equal to, this is by definition, summation N takes value 1 to infinity, absolute value of Sn minus Tn. And as in earlier problems or examples, we should have to introduce the third point or third sequence Un here by or without changing the value. So I shall write this as Sn minus Un plus Un minus Tn minus and plus, and we can prove this inside the absolute value. And further, this is by the property of absolute value function is less than or equal to summation mod of Sn minus Tn plus summation. We are separating these terms, and mod of or absolute value of Un minus Tn. And the first is exactly row of S and T, and the second is row of U and T. This is equal to row of S and T. Here I write equal to sign. Here it is less than or equal to. Here this term is exactly equal to this one, and this term is exactly equal to row of T and C. Sn minus C, it is to be corrected, Sn minus Un. Sn minus Un, and this is Un minus Tn. So this is row of S and U, and this is a row of U and T. And thus, so what we have, the left side is for this triangle inequality, the left side is row of S and T is less than or equal to, and this is less than or equal to, this last expression is row of S and U plus row of U and T. And thus all the four properties of a metric are verified. This proves the triangle inequality, and therefore this is a metric. Hence, a row is a metric. Row defined by this way is a metric. By this definition, is a metric for L1. The class or set of sequences such that summation mod of Sn is less than infinity. So this defines a metric, and this completes the solution. Now one more example we will have as a second problem from the exercise again. So I shall write, the problem is for P x1 y1 and Q x2 y2. These are 2 points. Obviously these are the points in R2. Define sigma of P and T is equal to absolute value of x1 minus x2 plus absolute value of y1 minus y2. So this sigma is a metric. order pairs of real numbers. And further, also if we defined another function tau of p and q is equal to maximum of absolute difference of x1 and x2 and absolute difference of y1 and y2. Show that tau is also a metric. Tau is metric for the same set. Above set of order pairs means R2. So this is a problem and we will consider its solution. We will solve it. So first we will show sigma is a metric. The metric may be denoted by rho, sigma, tau. Greek letters are used here, or sometimes it is also denoted by D. So the solution. Now first sigma is a metric. See the properties first. Three properties are obvious. We will consider let p x1 y1, or can be written like this, q x2 y2, order pair x2 y2, and r I shall consider order pair x3 y3. B in R2. So these are 3 points in R2. Then we have the following. First, sigma of P and Q by definition. See, it is absolute difference of, or absolute value of x1 minus x1, because we are considering the sigma between P and P. In place of P, Q, there is P, and therefore it is the definition is x1 minus x2 means difference in x coordinate plus absolute difference in y coordinate, y1 minus y2. So but if you consider P and P, then it will be the absolute difference of x1 and x1 plus absolute difference of y1 and y2. In place of x2 y2, there is x1 y1 again, and obviously this is 0. Second, if P is not equal to Q, then sigma of P and Q is absolute difference between x1 and x2 plus absolute difference between y1 and y2, and this is obviously greater than 0, because P is not equal to Q means either x1 is not equal to x2 or y1 is not equal to y2. That means one of them is not 0, means greater than 0. Third, sigma of P and Q is absolute difference of x1 and x2 plus absolute difference between y1 and y2. And but this can be written like this, and which is same as sigma of Q and symmetric property. And only remains is the triangle inequality, and for triangle inequality we have considered this P, Q and R. Now triangle inequality. Fourth, see here, to show triangle inequality we will consider sigma of P and T, and again it is by definition, or here it is absolute value of x1 minus x2 plus absolute value of y1 minus y2. And now we introduce the third point for this. that can be written as absolute value of x1 minus x3 plus x3 minus x2, and can be grouped, plus y1 minus y3 plus y3 minus y2. And by the property of absolute value functions, this is less than or equal to absolute value of x1 minus x3 plus absolute value of x3 minus x2 plus and now this can be grouped x1 minus x3 and plus absolute value of y1 minus y3, and this together gives this is equal to, or we can write like this, absolute value of x1 minus x3 plus absolute value of y1 minus y3 plus in another bracket absolute value of x3 minus x2 plus absolute value of y3 minus y2. And this, the first bracket is a row of x and P and R, because P is x1 y1 and R is x3 y3. So this is a row of P and R, and plus this is row of R and Q, and thus we have the left side is sigma of P, instead of row the metric here is sigma, so it is to be corrected. This metric is denoted by sigma, and thus we have the left side as sigma of P and Q is less than or equal to sigma of P and R plus sigma of R and Q, and thus sigma of P and Q is less than or equal to sigma of P and R plus sigma of R and Q. This verifies the triangle inequality, and hence this sigma is a metric. So thus we have verified the properties, 4 properties. So this completes the first part of the solution. Now see, the second example is tau of P and Q is maximum of absolute difference of x1 and x2 and absolute difference of y1 and y2. So this can be proved in similar manner. So I think you can try this yourself. Instead of this addition here, it is taken as maximum value between these two, and the properties can be verified exactly in the similar way. So you introduce for triangle inequality, introduce another R as having x3 y3 component. Here write this as x1 minus x3 plus x3 minus x2, and this also can be written in this form, and then this will be less than or equal to maximum of that. Only the word maximum will occur here, and this can be proved in a similar way. So please try this part yourself. The remaining part of this will continue in the next lecture. Thank you.